What if I told you that in the year 1816, snow fell across New England in the middle of June, crops froze in their fields during what should have been the height of summer, and families across the northern hemisphere faced a famine so severe that some resorted to eating their own livestock, hedgehogs, and even boiled nettles just to survive? This is not fiction. This is not myth. This happened. And the official explanation for this catastrophic event, while scientifically sound on the surface, may only be telling us half the story. The year 1816 has earned itself a haunting collection of names throughout history. In New England, survivors grimly referred to it as 1800 and froze to death. In German-speaking lands, the year that followed became known simply as the Year of the Beggar. But the name that has persisted most stubbornly in historical records is perhaps the most chilling of all: the year without a summer. It was a year when the natural order of seasons seemed to collapse entirely, when summer never truly arrived, and when humanity faced a climate disaster that would reshape societies, trigger mass migrations, and leave scars in the historical record that we are still trying to fully understand more than 2 centuries later. Let me paint you a picture of what people actually experienced during those dark months. On June 6th, 1816, a major snowstorm swept across the northeastern United States. This was not a light dusting. This was a full winter storm, complete with accumulating snow in regions where families had already planted their summer crops. Just days earlier, on June 5th, the town of Ipswich had experienced a heat wave that pushed temperatures to 92 degrees Fahrenheit. People had shed their winter clothing and celebrated the arrival of warm weather, but then a cold front descended with shocking speed. Within 24 hours, the temperature had plummeted to 43 degrees. It was not a gradual change. It was a meteorological whiplash that left farmers staring at their fields in disbelief. The cold did not relent. Throughout what should have been the growing season, frost returned night after night with devastating regularity. In Cape May, New Jersey, frost persisted for 5 consecutive nights in June. In upstate New York, farmers watched helplessly as their newly sprouted crops were frozen solid, forcing them to replant. Then, in July, those replanted crops froze again. The temperature would occasionally spike into the 90s, offering brief moments of hope, but then it would plummet to near freezing within just a few hours. Clothes hung on lines to dry froze solid in the summer air across New England. Ice formed on ponds and lakes in northwestern Pennsylvania in both July and August. And on the 4th of July, a day when Americans traditionally gathered outdoors to celebrate independence in the warmth of midsummer, witnesses reported ice forming an inch thick. John Quincy Adams, then serving as the United States Minister to Great Britain, wrote to his mother Abigail that there had scarcely been a single day in the entire year of 1816 when a fire was not needed in his home. This was summer in name only. The agricultural devastation was total. In May of 1816, frost had already killed off most crops in the higher elevations of Massachusetts, New Hampshire, Vermont, and upstate New York. When farmers attempted to salvage what they could and replant, nature struck again. By September, 4 severe frosts destroyed whatever corn had managed to survive the hostile summer. What little corn did grow never ripened. The grain that farmers desperately tried to harvest was consumed immediately, leaving nothing for seed to plant the following year. Famine became a very real threat throughout New England. The price of oats skyrocketed from 12 cents per bushel to 92 cents, an increase that put even basic sustenance out of reach for many families. There was not enough hay produced to feed livestock through the coming winter. Farm families faced an impossible choice and began slaughtering their cattle and horses, knowing they could not keep them alive. Some villages in Vermont descended into survival mode that sounds almost medieval. Residents were reported to have survived by trapping and eating hedgehogs and by boiling nettles, a weed, for sustenance. But this was not merely an American tragedy. The entire Northern Hemisphere was gripped by the same inexplicable climate anomaly. In Europe, the situation was equally desperate, and in some regions even worse. In Ireland, torrential rains flooded fields, and the potato crop, a staple food source, rotted in the ground. Widespread starvation followed, and a typhus epidemic swept through the weakened population, killing thousands in the years that followed. In England, France and Germany, wheat crops failed on a massive scale. Bread, the fundamental food of European societies, became scarce and prohibitively expensive. Food riots erupted across the continent. In the East Anglian counties of England, desperate labourers rose up in armed protest as early as May 1816. They marched under flags emblazoned with the chilling demand, bread or blood. In one notable incident, these protesters marched on the cathedral town of Ely, took magistrates hostage, and engaged in a pitched battle with the local militia. The army was deployed to suppress similar disturbances in Scotland and Wales. Provincial jails across the kingdom filled beyond capacity with rioters, many of whom were subsequently executed or transported to penal colonies. In Switzerland, conditions deteriorated so severely that survivors documented eating moss, sorrel, and even animals not typically considered food to stay alive. Germany saw mortality rates in 1817 climb more than 50% higher than they had been even during the war year of 1815. Everywhere, desperate villagers resorted to what contemporary accounts described as the most loathsome and unnatural foods: carcasses of dead animals, cattle fodder, leaves of nettles, swine food. This was not poverty. This was societal collapse, driven by the failure of nature itself. The crisis extended far beyond Europe and North America. In northern China, the climate disruption caused crop failures that led to mass starvation, with thousands of people dying. In southern Asia, the unusual weather patterns triggered torrential rains that in turn sparked a cholera epidemic, which killed vast numbers of people. This was a truly global catastrophe, one that affected every inhabited continent and left deep scars on societies that would take years, sometimes decades, to heal. The demographic impact was staggering. In New England, the year without a summer sparked one of the earliest large-scale westward migrations in American history. As families abandoned their failed farms and sought better fortune in the undeveloped territories of the Midwest, entire communities picked up and moved, driven by the simple fact that they could no longer survive where they were. Now, here is where the official story becomes both compelling and, upon closer examination, strangely incomplete. Modern science attributes the year without a summer to a single volcanic eruption. On April 10th, 1815, Mount Tambora, a volcano located on the island of Sumbawa in present-day Indonesia, erupted with a violence that almost defies comprehension. It was one of the most powerful volcanic eruptions in recorded human history, classified as a VEI 7 event on the Volcanic Explosivity Index, a logarithmic scale where each step represents a tenfold increase in power. The eruption began in the evening around 7 o'clock, with a Plinian column of ash and gas that shot 40 kilometres into the atmosphere, far higher than commercial aircraft fly today. For 3 hours, pumice and ash rained down continuously. Then the eruption column collapsed, sending massive pyroclastic flows, rivers of superheated gas and rock, racing down the slopes of the mountain at devastating speed. These flows were so powerful that they travelled over the ocean itself and triggered a destructive tsunami 4 metres high. The eruption obliterated more than 1,400 metres of the mountain's height, leaving behind a caldera 6 to 7 kilometres wide and 6 to 700 metres deep. Approximately 41 cubic kilometres of magma were ejected into the atmosphere. Ash falls covered islands hundreds of kilometres away, with deposits 20 to 50 centimetres thick. In some places, people thought gold was falling from the sky and collected the ash to sell as medicine. But it was not the ash that caused the global climate disaster. It was the sulphur. Tambora released massive quantities of volcanic sulphur gases into the stratosphere. These gases converted into tiny droplets of sulfuric acid that spread around the entire planet, forming an aerosol cloud the size of Australia. This cloud acted like a mirror in the sky, reflecting sunlight back into space before it could reach the Earth's surface. The result was a drop in global temperatures estimated at between 1 and 3 degrees Celsius. That might not sound dramatic, but when applied globally and sustained over months, a temperature drop of even 1 degree is enough to devastate agriculture, disrupt weather patterns, and plunge entire regions into crisis. Global precipitation decreased by 4% in 1816. The combination of colder temperatures and disrupted rainfall patterns created the perfect conditions for crop failures across multiple continents simultaneously. The connection between Tambora and the year without a summer is now accepted science. The evidence is solid. The timeline matches. The mechanism is well understood. Volcanic winters caused by major eruptions are a known phenomenon. Everything about this explanation is reasonable, logical, and backed by both historical records and modern climate modelling. So why are we even questioning it? Because there is something that does not quite fit, something that the official narrative glosses over or explains away, with assumptions that, when examined closely, begin to look less like answers and more like polite avoidances of deeper questions. If Tambora alone caused the catastrophic climate of 1816, then we should expect the climate disruption to have been relatively short-lived. Volcanic aerosols in the stratosphere typically remain aloft for 1 to 3 years before dispersing and settling out of the atmosphere. Yet the accounts from 1816 describe not just a bad summer, but a systemic breakdown of expected weather patterns that some records suggest had already been underway before Tambora even erupted. There are hints in historical documents of unusual weather in the years immediately preceding 1816, patterns that do not fit neatly into the Tambora-only explanation. Moreover, if a single volcanic event could cause such widespread devastation so quickly, why do we not see more examples of similar climate collapses following other large eruptions? Tambora was enormous, yes, but it was not the only major eruption in human history. What made 1816 different? Was Tambora merely the final blow to a climate system that was already weakened or disrupted by something else, something that happened earlier and has been overlooked or misunderstood? There is another question that demands attention. The global response to the year without a summer was not merely one of surprise. It was one of profound shock and disorientation. People did not simply say, "The volcano erupted, and now the weather is bad." They did not have that framework. Most people in 1816 had no idea that a volcano had erupted on the other side of the world. They experienced the climate disaster as an inexplicable act of nature, a biblical scale punishment, or a sign of the end times. The psychological and social impact of the event suggests that this was not perceived as a temporary anomaly, but as a fundamental break with the normal order of the world. Why did it feel so catastrophic? Why did entire societies seem on the verge of collapse? Was it only because of one bad summer? Or were populations already stressed? already living on the edge of subsistence because of prior disruptions that we have not fully accounted for. This investigation is not about denying the science of Tambora. The eruption happened, the volcanic winter happened, the connection is real. But what if Tambora was not the beginning of the story? What if it was the climax of a longer, more complex chain of events? What if the year without a summer was not an isolated disaster caused by a single volcanic eruption, but rather the final, most visible symptom of a global climate disruption that had been building for years, perhaps even decades, before 1816? If that is true, then the real question is not what Tambora did to the climate. The real question is, what was already happening to the climate before Tambora erupted, and why has that part of the story been so quiet in the historical record? We are going to find out. Over the course of this investigation, we will examine the evidence that exists outside the standard narrative. We will look at climate records from the years and decades leading up to 1816. We will analyse the patterns of volcanic activity, solar behaviour, and atmospheric conditions that framed the disaster. And we will ask whether the official explanation, while accurate in its details, might be incomplete in its scope. By the end, you will have the information needed to decide for yourself whether the year without a summer was truly a one-time event triggered by a single cause, or whether it was the culmination of something far larger and more troubling. The data is there. The records exist. We just need to look at them with fresh eyes and a willingness to ask uncomfortable questions. Let's begin. The mystery deepens when we examine what happened in the years immediately before 1816. The official narrative treats Tambora as a singular catastrophic event, an isolated eruption that struck a stable climate system and temporarily disrupted it. But this interpretation requires us to overlook a crucial detail hidden in ice core data and historical records. Scientists have found evidence of a massive volcanic eruption that occurred in 1808 or 1809, an eruption so significant that its sulfur signal appears in ice cores from both Greenland and Antarctica with clarity that rivals Tambora itself. This eruption, sometimes called the unidentified 1809 eruption, or colloquially Mountain X, was so powerful that it injected somewhere between 12 and 19 metric tons of sulfur dioxide into the stratosphere. To put this in perspective, it was responsible for nearly as much atmospheric cooling as Tambora would be 6 years later. Yet very few people have ever heard of it. Historical records from around 1809 and 1810 describe unusual weather patterns and temperature anomalies that are typically glossed over in favour of focusing exclusively on Tambora. Tropical temperatures showed a significant drop in 1809 and 1811, a cooling that is generally considered on par with the post-Tambora cooling of 1816 and 1817. Northern Hemisphere summer temperatures were abnormally cold during this period as well. Tree ring records from northwestern North America, some of the most sensitive and precise climate proxies available to scientists, show that 1810 was an exceptionally cold year, ranking as the coldest year recorded in several regional chronologies. The Indo-Pacific warm pool, a crucial region for global ocean temperatures, experienced profound cooling from 1809 to 1812, with temperature anomalies between minus 0.28 and minus 0.79 degrees Celsius. Yet the standard history books barely mention these events. They are treated as minor background noise, prelude to the real climate disaster of 1816. What we are looking at here is not a single climate shock, but a double hammer blow delivered by nature to an unprepared world. The first blow came from the 1809 eruption. The second, much more violent blow came from Tambora in 1815. Between these two major eruptions, global temperatures remained depressed, precipitation patterns disrupted, and agriculture stressed. By the time 1816 arrived, the global climate system had already been struggling for 6 or 7 years. Populations had already experienced lower yields, food shortages, and social stress as a consequence of the earlier cooling. Then Tambora erupted, and the system collapsed entirely. This is not to say that Tambora was not catastrophic. It absolutely was. But to understand why 1816 became the year without a summer rather than merely a bad year like 1810 or 1811, we must account for the fact that the event occurred in a climate system that was already weakened, already unstable, already running on fumes. But the volcanic activity of the early 1800s did not consist solely of these two major eruptions. Between 1809 and 1815, a series of smaller eruptions occurred around the world. In 1814, the Mayon volcano in the Philippines erupted. Between 1812 and 1813, eruptions occurred in the Ryukyu Islands, in Indonesia, and in the Caribbean. These eruptions may have been individually less powerful than Tambora or the 1809 event, but cumulatively they added to the atmospheric aerosol load. They contributed to the cooling trend that had begun in 1809. They kept temperatures suppressed year after year. The effect was one of accumulation, each eruption preventing the atmosphere from fully recovering before the next one struck. This pattern of volcanic activity was not random or unusual in isolation. What was unusual was the frequency and the clustering. Multiple major eruptions in a short time period is not common in the historical record, but the early 1800s experienced what scientists call a volcanic cluster. This period saw more powerful volcanic eruptions in closer succession than is typical. The question we must ask is whether this clustering itself was random, or whether it was a symptom of something deeper happening within the Earth's geological systems. But volcanic activity was not the only natural forcing at work. At precisely the same time that multiple major volcanoes were erupting, the Sun itself was experiencing an unusual period. The early 1800s fell within what is called the Dalton minimum, a period of significantly reduced solar activity that lasted from approximately 1790 to 1830. During this period, the number of sunspots visible on the Sun's surface was roughly 1/3 of what is normally observed during typical solar cycles. Sunspot activity is an indicator of overall solar energy output. Fewer sunspots correlate with slightly lower solar radiation reaching Earth. This reduction was subtle on an individual year basis, but sustained over decades, the cumulative effect of reduced solar output during the Dalton minimum may have been significant. Here is where the climate picture becomes genuinely complex. The official explanation for the year without a summer focuses exclusively on Tambora and argues that this single eruption was sufficient to explain the severity of the climate disaster in 1816. But this explanation ignores the broader context in which Tambora occurred. The eruption did not strike a climate system operating under normal solar activity. It struck a climate system that was already receiving slightly less solar energy due to the Dalton minimum. Moreover, Tambora did not erupt into a pristine atmosphere. It erupted into an atmosphere that was already laden with aerosols and sulfate particles from the 1809 eruption and from subsequent volcanic activity. The cooling from these earlier eruptions had not fully dissipated. The greenhouse effect of Earth's atmosphere had already been slightly reduced by lower solar output, and then into this already stressed system came Tambora, the most powerful eruption of the era. The interaction of multiple forcing factors is known in climate science as a multiplicative effect. Each factor alone might produce a modest climate impact, but when they occur simultaneously, their effects interact with and reinforce each other, producing an outcome more severe than the sum of the individual parts. It is the difference between a patient who is healthy and encounters a single illness, and a patient who is already weakened by chronic disease and then encounters the same illness. The outcome is catastrophically different. This multiplicative model fits the evidence far better than the single cause explanation offered by the mainstream narrative. Tambora was indeed the largest eruption, the most direct cause of the year without a summer, but Tambora's impact was magnified, amplified, and made infinitely more devastating by the climate conditions that already existed. Consider what this means for our understanding of the event. When the temperature plummeted in 1816, people experienced not the direct effect of a single eruption that occurred a few months earlier, but rather the combined cooling effect of a solar minimum, multiple years of atmospheric loading from volcanic eruptions, and the fresh injection from Tambora. Each of these factors reduced global temperatures somewhat. Together they created a synergistic cooling that was far more severe than any of the factors would have been in isolation. The crops failed not because the sun was slightly dimmer. They failed not because the 1809 eruption had lingered in the atmosphere. They failed because all of these things happened together in a deadly convergence. This reframing of 1816 as the culmination of a multi-year climate disruption, rather than as an isolated catastrophe, has important implications. It suggests that the true beginning of the climate crisis was not April 1815, when Tambora erupted. The true beginning was in 1809, with the unidentified eruption. The crisis that people experienced in 1816 was actually the endpoint of a 7-year sequence of global cooling. This also suggests something more unsettling. If 1816 was the result of cumulative climate stresses, then the question becomes what other major historical events might have actually been the visible culmination of longer processes that we have not recognised because our historical analysis tends to focus on single dramatic events. But there is another layer to this mystery, one that concerns the very nature of the data we are working with. Ice core records, tree rings, and other paleoclimatic proxies provide us with a window into past climate, but these records have limitations. There are gaps. There are years where multiple regions experience strange weather that was never formally recorded or was recorded in sources that have been lost to history. The historical record itself is incomplete. We have observations from ships, from scientific instruments, from personal diaries of educated people living in the right places. But we do not have systematic global temperature measurements for most of the world during this period. We are seeing the climate through a fragmentary lens. We know that something very significant happened in 1809. We can see it in the ice, but we do not have a complete picture of how severe the climate disruption actually was because the global observational network of the time was sparse and scattered. What if the climate stress of the period before 1816 was even worse than the ice core records suggest? What if there were additional disruptions, additional cooling events, additional stresses on global agriculture that left no permanent mark in the ice or in the trees because they were localized or temporary? The historical records from the years 1810 through 1815 do mention unusual weather events. There are scattered reports of cold, of frosts, of crop problems in various parts of the world. But these reports are anecdotal. They come from different sources with different standards of documentation. They are difficult to synthesize into a unified picture of global climate. Yet when we compile these scattered reports, a pattern begins to emerge. The years before 1816 were not normal. They were climatically unstable. The world was not in a state of equilibrium, waiting for Tambora to knock it off balance. The world was already rocking back and forth, already struggling, when Tambora struck. The narrative of the year without a summer that dominates in textbooks and scientific literature is not wrong. It is simply incomplete. Yes, Tambora caused catastrophic cooling. Yes, the volcanic winter of 1816 was the most visible, most dramatic, most measurable result of that eruption. But Tambora was not a beginning. It was an ending. It was the final collapse that came after years of stress. Understanding this changes how we evaluate the historical significance of the period and how we think about climate resilience and vulnerability. When systems are already stressed, when they are already operating at the edge of stability, even a moderately large shock can become catastrophic. This is a principle that applies not only to the climate of 1816, but to any complex system pushed to its limits. But the evidence of pre-1816 climate stress is not merely theoretical or confined to ice cores and tree rings. We have hard historical evidence of suffering, of famine, of social collapse occurring in the years before Tambora even erupted. This evidence has been systematically underemphasized in most accounts of the year without a summer, relegated to footnotes or treated as coincidental background noise. Yet when we examine the historical record carefully, a pattern of crisis emerges that spans nearly a decade and a half. Korea provides perhaps the clearest example of this pre-Tambora climate catastrophe. Between 1809 and 1810, a severe famine swept through the Joseon dynasty, a famine so catastrophic that it killed approximately 7.8% of the total population, roughly 14 million people. This famine, known as the Kigyeong famine, was caused by an unprecedented drought that struck in June and July of 1809, during the critical months when rice and barley crops needed moisture to thrive. The precipitation during June and July 1809 dropped by more than 73% in some months, a catastrophic deficit. All autumn crops withered and died. No seeds were left for planting the following year. Starvation followed. Then, just 4 years later, in 1814 and 1815, Korea was struck by yet another severe famine, the Kabul famine, which killed approximately 17.8% of the population. Again, it was caused by a severe drought in June and July. Again, all the crops failed. Again, starvation consumed the nation. This was not a single disaster. This was a pattern. 2 massive famines, separated by only 4 years, both caused by similar patterns of precipitation failure in the same months of the year. The probability of such a pattern occurring by chance is extraordinarily low. What is particularly striking about these Korean famines is their timing. The first famine of 1809 and 1810 corresponds precisely with the period of global cooling from the unidentified 1809 eruption. The second famine of 1814 and 1815 occurs in the immediate years before Tambora. The Korean historical record was meticulous. The government maintained detailed records of grain harvests, of starvation, of relief efforts. The documentation is extensive and undeniable, and it shows that severe agricultural disruption caused by climate anomalies was already occurring years before 1816. The world was already in crisis before Tambora struck. Nor was Korea alone. In 1811 and 1812, Spain experienced a devastating famine. The city of Madrid was particularly hard hit, with an estimated 20,000 deaths. The famine was caused by agricultural failure, a failure that had multiple causes, including warfare and economic disruption. but one that climate stress clearly contributed to. In England and Scotland, historical records document severe agricultural stress in the years leading up to 1816. Tree ring data from northwestern North America shows persistent and extreme cold anomalies in the years immediately following the 1809 eruption. The Gulf of Alaska, the Wrangell St. Elias Mountains, and southern Yukon experienced particularly pronounced cooling during 1809 and the subsequent years. This means that the North American continent was already colder, already experiencing suppressed growing seasons before 1816 arrived. The broader climate context is crucial. Between 1809 and 1815, the world experienced what we might call a period of recurring climate shocks. No single year was quite as catastrophic as 1816, but year after year the weather was wrong. Crops that should have thrived produced poor yields. Frosts came at unusual times. Precipitation patterns were erratic. In some regions, droughts plagued the land. In others, excessive rains damaged crops and caused flooding. The agricultural system, which depends on consistency and predictability, was receiving neither. Farmers were accustomed to the occasional bad year, but a succession of bad years, stretching across half a decade, pushed communities to the edge of collapse. By the time 1816 arrived, many regions were not simply experiencing a climate disaster. They were experiencing the final breakdown of a system that had been under sustained stress for years. This accumulation of stress is the crucial missing element in most accounts of the year without a summer. The narrative focuses on 1816 and Tambora, treating the preceding years as essentially normal background. But for people living through the 1810s, the preceding years were not normal at all. Farmers in Europe had experienced poor harvests in 1810, 1811, 1812, and again in 1814 and 1815. Food supplies had been depleted. Granaries were not full. People were already malnourished, already weakened. The social fabric was already frayed from years of economic stress and food scarcity. Then came 1816. Then came absolute failure. The result was not merely famine, but societal near collapse. The social unrest that erupted in 1816 cannot be fully explained without understanding the decade that preceded it. In England, the bread riots that began in May of 1816, where desperate labourers marched with flags declaring bread or blood, occurred in a country that had already endured nearly a decade of elevated food prices, economic hardship, and sustained population stress. The enclosure movement, which had consolidated agricultural lands into the hands of wealthy landowners, had left the rural poor without access to commons where they could forage or keep livestock. Food prices had been rising since the 1790s, doubling in cost multiple times. The government had passed the Corn Laws in 1815, restrictions on grain imports intended to protect domestic producers, but which in 1816 ensured that there would be no relief from foreign supplies. The combination of pre-existing economic hardship, the failure of the harvest, and the government's protectionist policies created an explosive situation. By June of 1816, riots had erupted not just in England but across Europe. In France, which was still reeling from the trauma of the Napoleonic Wars and the Bourbon Restoration, the food shortages created the sense of a nation on the edge of anarchy. Regional riots in the provinces intensified with each month. The fear of revolution haunted European leaders. What is remarkable about these riots is that they were not reactions to Tambora directly. Most people in 1816 had no idea that a volcano had erupted on the other side of the world. Many people had not even heard of Mount Tambora. What they knew was that food was scarce and prices were catastrophic, and they knew that this problem had been building for years. The riots of 1816 and 1817 were described at the time as the most violent period of civil unrest in Europe since the French Revolution, but they were not the inevitable consequence of a single event. They were the eruption of a pressure that had been building steadily for nearly a decade. We must ask ourselves, why is this period of pre-Tambora climate stress so absent from the conventional narrative of the year without a summer? Why do textbooks present 1816 as though it emerged from a climate system that was previously stable and predictable? The answer, in part, is methodological. Modern climate science focuses on major eruptions as the primary driver of climate change in historical periods. When researchers examine the 1809 eruption, they notice its signature in ice cores, they measure its cooling effect, and they move forward. When they examine Tambora, they find a much more dramatic signal and focus their attention there. The periods of climate stress before 1816 exist in scattered historical records that are less visually striking than ice cores or volcanic ash layers. They exist in Korean grain records, in English newspaper accounts of bread riots, in the personal correspondence of farmers and government officials. These sources are harder to synthesize into a single unified picture of global climate. So the narrative simplifies. It focuses on the volcano. It treats 1816 as an isolated crisis. And in doing so, it misses a crucial truth, that 1816 was not the beginning of anything. It was the culmination. Consider the implications of this reframing for our understanding of climate vulnerability. A climate system that is stable and operating within its normal range of variation has a certain capacity to absorb shocks. A single powerful eruption striking a stable system will cause disruption, but the system can recover. But a climate system that is already stressed, already operating at the edge of its parameters, can be tipped into collapse by the same shock. The decade before 1816 was exactly such a period. Multiple volcanic eruptions reduced solar output from the Dalton minimum, and the cumulative aerosol loading in the atmosphere had already pushed global temperatures below their long-term mean. Precipitation patterns had already been disrupted. Agricultural yields had already been suppressed. The global food system was already struggling. Then, into this weakened state came Tambora. This pattern has implications that extend far beyond historical curiosity. It speaks to a principle of complex systems that applies to climate, to agriculture, to economics, and to human societies themselves. When multiple stresses act upon a system simultaneously over an extended period, the system does not degrade linearly. Instead, there is a tipping point, a moment where the accumulated stress causes sudden, catastrophic failure. The system may appear to be functioning adequately right up until the final shock arrives, but the system is not actually stable during this period. It is in a state of marginal stability, held together by the remaining reserves of its capacity, vulnerable to even a moderately large perturbation. Tambora was that perturbation. But Tambora was only catastrophic because of the 7 years of prior stress that preceded it. Furthermore, the evidence from the decade before 1816 demonstrates something else entirely. It shows that we cannot understand major historical events by looking at single causes in isolation. The year without a summer is presented in school textbooks as though it has a single explanation. Mount Tambora erupted, the temperature dropped, crops failed, the end. But the reality is far more complex. The 1809 eruption, the series of lesser eruptions that followed, the reduced solar output of the Dalton minimum, the pre-existing economic disruption from the Napoleonic Wars, the structure of the global food system, and its vulnerability to regional crop failures, the accumulated stress on populations already weakened by prior hardship, and finally, the violent eruption of Tambora in 1815, all of these factors interacted to produce a catastrophe far more severe than any single factor would have caused. History is not determined by single events. It emerges from the convergence of multiple forces. This brings us to a question that historians and climate scientists have not adequately addressed. If the world was already suffering from climate stress in the years before 1816, how much of what happened in 1816 was actually caused by Tambora, and how much would have happened anyway due to the pre-existing climate disruption? This is not a simple question to answer, but it is a crucial one, because if significant famine and social disruption would have occurred in 1816, regardless of Tambora, then we must revise our understanding of Tambora's responsibility for the year without a summer. We must acknowledge that Tambora was not the sole cause of the crisis. Tambora was the culminating event in a longer chain of climate and social disruption. The volcano made things catastrophic, but the catastrophe was already in the making. The physical mechanisms that made the year without a summer so catastrophic were not limited to temperature and precipitation. The climate disruption triggered a cascade of secondary effects that amplified the initial shock and transformed what might have been a severe agricultural crisis into a societal collapse. These cascading effects reveal the degree to which the global system is interconnected, and how a disruption in one domain can reverberate through multiple systems simultaneously. The first cascading effect was the disruption of ocean circulation patterns. Volcanic aerosols in the stratosphere did not merely reflect sunlight and cool the atmosphere. They altered the fundamental energy balance that drives ocean currents. The Atlantic meridional overturning circulation, which includes the Gulf Stream, experienced disruption during the years of high volcanic aerosol loading. Changes in surface ocean temperature and salinity, drove by anomalous precipitation patterns, affected the density gradients that drive thermohaline circulation. The Gulf Stream, which transports warm tropical water northward and provides Western Europe with a climate substantially warmer than it would otherwise experience, weakened during the critical period. This meant that Europe, which was already experiencing colder temperatures from the volcanic aerosol effect, suffered an additional cooling as the moderating influence of the Gulf Stream diminished. The temperature anomalies were not uniform. Some regions experienced catastrophic cooling far beyond the global average. This differential regional impact is a crucial detail often overlooked in simplified narratives of the year without a summer. The cooling was not simply a global blanket of reduced temperature. It was a disruption of the normal patterns of energy transport that kept certain regions habitable and productive. The second cascading effect was the destabilization of regional precipitation patterns on a continental scale. The aerosol veil over the planet disrupted the jet streams, the fast-moving rivers of air that guide weather systems. Monsoon patterns in Asia were disrupted, leading to either excessive rainfall or droughts depending on the specific region and the specific year. In South Asia, the climate anomaly of 1816 triggered an unprecedented sequence of droughts and flooding. This alternation between extremes created the perfect conditions for the emergence of a new, highly virulent strain of cholera. The cholera bacterium, which had long been endemic to the Bengal region, thrived in the warm waters of the Bay of Bengal, but the disrupted climate patterns altered the microbial ecology of those waters. The unusual temperature fluctuations, the changes in salinity caused by altered precipitation, and the disrupted seasonal patterns created conditions that allowed a new strain of the disease to emerge and rapidly spread. By late 1816 and into 1817, the first modern cholera pandemic began. What started as an altered precipitation pattern became a global plague. The disease spread from Bengal across Asia, reaching China, Southeast Asia, and the Middle East within a few years. It killed hundreds of thousands, perhaps millions, across multiple continents. The cholera pandemic that ravaged Asia, Europe, and eventually the entire world for decades to come had its origins in the climate disruption caused by Mount Tambora. Climate altered the disease environment, which in turn killed millions of people who had nothing to do with volcanism and never knew that a volcano had caused their suffering. The third cascading effect was even more immediate and direct. When crops failed across entire regions due to frost and cold, and when famine became widespread, populations became malnourished. Malnourished people are immunocompromised. Their bodies cannot fight off infections effectively. At precisely the moment when food was scarcest, disease emerged with devastating force. In Ireland, the crop failure of 1816 meant that families had insufficient food for winter. Malnutrition set in. Then, in 1817, as populations weakened by hunger, struggled through the cold winter months, a typhus epidemic erupted. Typhus, transmitted by lice, thrives in crowded, unsanitary conditions where people cannot bathe regularly due to cold and fuel scarcity. Between 1816 and 1819, major typhus epidemics swept through Europe, including Ireland, Italy, Switzerland, and Scotland. More than 65,000 people died from typhus in Ireland alone. The epidemic was as much a consequence of famine as it was an independent disease event. People died not only from starvation, but from the infectious diseases that the climate catastrophe enabled. The scale of disease mortality was staggering. The first cholera pandemic of 1817 to 1824 killed an estimated 100,000 people or more across Asia and eventually touched Europe. The exact death toll is impossible to determine because many deaths in remote regions were never recorded. But we have specific documented examples of the pandemic's devastating power. In Basra, Iraq, an estimated 18,000 people died in less than a month's time during 1821. In Vietnam, Royal Archives recorded that 206,835 people died from the disease. In Java, over 100,000 deaths were documented. And these are only the cases where documentation exists. The true global death toll from the cholera pandemic may have been several million. A pandemic that would ultimately define the 19th century, killing tens of millions before being brought under control, originated in the climate catastrophe of 1816. But there is another consequence of the cascading effects that deserves attention, one that is often overlooked in narratives focused on immediate deaths and famines. The year without a summer and its aftermath fundamentally altered the trajectory of human history and global power structures. In China, the famine and climate stress of 1816 and the following years drove desperate farmers to seek alternative crops that might provide more reliable income. Opium, which had previously been relatively uncommon in most of China, offered the promise of consistent profitability even in difficult climate years. Within a few decades, opium cultivation had spread throughout Yunnan province in southwest China. The agricultural knowledge and processing technology spread into the mountains of Burma and Laos, creating what would become known as the Golden Triangle of international drug production. This development would eventually contribute to the Opium Wars, the fall of the Qing dynasty's power, and the subjugation of China to Western colonial interests. One could argue that the modern trajectory of China's relationship with the West, and by extension the entire history of 19th and 20th century Asia, traces back partially to the climate disaster of 1816. In Europe, the social and political consequences were equally profound. The bread riots and armed uprisings of 1816 and 1817 demonstrated the brittleness of political structures that could collapse when food supplies failed. European governments learned a lesson from this crisis. They began implementing protectionist trade policies, tariffs designed to protect domestic agricultural production and prevent food prices from falling below levels that could sustain local farmers. These protectionist policies, which first emerged as responses to the 1816 crisis, became permanent features of the European economic system. They contributed to the rise of nationalism, to trade barriers between nations, and to the economic tensions that would eventually explode into the catastrophic wars of the 20th century. The year without a summer was thus not merely a climate crisis. It was a watershed moment that altered the trajectory of global politics and economics in ways that reverberated for centuries. The fourth cascading effect was psychological and cultural. The year without a summer was experienced by people who had no scientific framework to explain what was happening. They did not know about volcanic eruptions on the other side of the world. They did not understand aerosol physics. They experienced the climate disaster as an inexplicable act of divine punishment, a sign that God had withdrawn his favour from humanity, or a portent of the end times. In literature and art, the crisis left deep marks. Mary Shelley, the young daughter of philosophers and scientists, was living in Geneva during the summer of 1816. The perpetual gloom, the cold, and the social desperation surrounding her provided the darkest inspiration for her novel Frankenstein, one of the most influential works of English literature. A work that has influenced how humans think about science, ambition, and the unintended consequences of human actions ever since. The psychological impact of the year without a summer manifested itself in the Romantic movement in art and literature, a movement characterized by emphasis on emotion, nature, and the sublime terror of natural forces beyond human control. The cultural products of the 19th century, the novels and paintings and poetry that we revere today, were shaped in part by the trauma of 1816. This brings us to a crucial realization. The year without a summer was not merely a climate anomaly followed by recovery. It was a moment of fundamental disruption to multiple interconnected systems. Climate, agriculture, disease, ecology, ocean circulation, social order, political structures, and human consciousness. The eruption of Mount Tambora did not simply cause cooler temperatures. It triggered a cascade of effects that reshaped continents, altered the emergence and spread of diseases, redirected the course of human history, and left psychological scars on entire civilizations. Each of these cascading effects amplified the initial disruption. A climate anomaly became a food crisis. The food crisis enabled disease. Disease weakened populations further. The combination of hunger and disease destabilized societies. Political instability drove changes in trade policy and agricultural practice. Those changes, in turn, altered the trajectory of human development for generations to come. What becomes clear when we examine these cascading effects is that the distinction between cause and effect becomes blurred when we zoom out to examine the full scope of historical causation. Was the year without a summer caused by Tambora? Yes, in the direct sense that the eruption injected aerosols into the atmosphere and reduced solar radiation. But was it caused by the Dalton minimum and the prior volcanic activity? Yes, in the sense that these factors weakened the climate system and reduced its resilience. And was it caused by the global food system's vulnerability to regional crop failures? Yes, in that the interconnectedness of trade meant that famine, in one region could trigger famine in others? And was it caused by the microbial ecology of the Bay of Bengal and the mutation of the cholera bacterium? Yes, in that the disease pandemic was an inevitable consequence of the climate disruption. When we step back and examine the full chain of causation, we realise that history is not determined by single events. History emerges from the interaction of multiple systems, each operating according to its own logic, but all connected through networks of cause and effect that we are only beginning to understand. This understanding has profound implications for how we think about our own time. Today we face a warming climate, not a cooling one. We face disruptions to agricultural systems, disease patterns, and ocean circulation caused by anthropogenic greenhouse gas emissions rather than by volcanic eruptions. We face the prospect of cascading effects we may not even foresee. But the year without a summer teaches us something crucial, that the visible crisis is rarely the true beginning of the disruption. The true beginning is often hidden in gradual changes that precede the dramatic event, and the true consequences of a disruption often extend far beyond the immediate impact that we measure and count. They ripple outward through interconnected systems, creating second and third order effects that reshape the world in ways that no one predicted when the initial disruption began. We now arrive at the culminating truth that emerges from examining the year without a summer, not as an isolated historical event, but as a complex convergence of climate, biology, economics, and human society. The mystery that began with a simple question, why was 1816 so catastrophic, has expanded into an investigation of how multiple systems interact, how hidden vulnerabilities in supposedly stable structures can be exposed, and how a disruption that seems localized can ripple outward to reshape the world. But before we conclude, we must address the question that frames this entire investigation. What happened after the 1816? And what does that tell us about the nature of climate disruption and human recovery? The recovery from the year without a summer was neither swift nor uniform. By 1818, the volcanic aerosols had largely dispersed from the stratosphere, and normal solar radiation began reaching the Earth's surface again. Temperatures rose. But the return to climatic normalcy did not mean a return to social normalcy. The disruptions had set in motion cascades of consequence that would continue unfolding for years. In 1817 and 18, Europe still experienced food shortages and elevated prices as populations worked to rebuild grain reserves, and farmers attempted to restore agricultural productivity after 2 years of failure. The cholera pandemic that had emerged in response to the disrupted climate of Bengal continued its relentless spread, eventually reaching Russia and Europe by 1819 and 1820. The disease would recur in waves throughout the 19th century, killing millions before being brought under control. The physical climate had stabilised, but the biological and social disruptions it had triggered continued their own momentum. This is a crucial observation. Climate events have consequences that persist long after the physical disruption has ended. The disease ecology altered by 1 year of climate stress generates pandemics that kill for decades. Economic stress that triggers population migrations sets in motion social changes that reshape political structures for generations. The visible crisis is not the true measure of the damage. The true damage extends far into the future, following pathways and mechanisms that we discover only with hindsight. In 1818, something remarkable occurred in Switzerland. An ice dam formed by the Gietro Glacier in the Val de Bagnes, created by the exceptional cold and snowfall of 1816 and 1817, collapsed catastrophically. Engineer Ignaz Venetz had warned that the dam was unstable and might burst. Despite his attempts to drain the expanding glacial lake, the structure could not hold. In June 1818, the dam gave way, releasing a wall of water that roared down the valley, destroying everything in its path and killing 40 people. This flood was not a direct result of the eruption of Tambora. It was an indirect consequence, a delayed effect triggered by the abnormal accumulation of ice during the years of climatic disruption. The year without a summer created conditions that persisted for years after the initial climate shock had passed. This is how nature works at the scale of years and decades. Systems have memory. Disruptions create conditions that continue to generate consequences long after the original cause has ceased. The recovery process also revealed something profound about human resilience and adaptation, but also about the fragility of societies that depend on stable agricultural systems. Farmers had learned from the catastrophe. They began diversifying their crops, planting varieties that were more cold resistant and could be harvested more quickly. They improved storage techniques and began to build larger grain reserves. Agricultural technology advanced more rapidly after 1816 than it had in the preceding decades, driven by the knowledge that climate could fail and society needed to be prepared for that possibility. The westward expansion of the United States, which was accelerated by the year without a summer, as families abandoned failed farms in New England for new opportunities in the Midwest, created populations dispersed across a larger geographic area. This geographic diversification meant that future crop failures in one region could potentially be mitigated by surplus production in another region. The global food system became more complex and interconnected, creating both resilience and vulnerability. It became more resilient in the sense that regional crop failures could be mitigated by trade, but it also became more vulnerable in the sense that disruptions in major growing regions could affect distant populations that depended on trade. The globalization of agriculture, which accelerated in the 19th century, was partly a consequence of learning lessons from 1816, but perhaps the most important consequence of 1816 was that it demonstrated the potential for climate to disrupt global systems. Before 1816, most educated people believed that climate was essentially stable. Local variations occurred, but the climate was fundamentally reliable and predictable on a global scale. The year without a summer shattered this assumption. The world learned that climate could change in ways that could not be predicted in advance, that distant events on the other side of the planet could have catastrophic local consequences, and that human societies, despite their complexity and apparent stability, were vulnerable to forces beyond their control. This realization, though not widely articulated at the time, began to reshape how governments thought about food security, trade policy, and the relationship between climate and civilization. Now we arrive at perhaps the most disquieting question raised by this investigation. The year without a summer is presented in modern scientific literature as the climatic event of 1816 itself, a crisis that lasted for roughly 2 years and then passed. But we have seen that the true disruption lasted much longer. The cascade of climate stress that began with the 1809 eruption did not truly end until well into the 1820s, when the effects of the cholera pandemic had fully manifested and the secondary consequences of migration and economic disruption had played out. Moreover, we have discovered that the crisis of 1816 was not a singular event caused by a single eruption. It was the culmination of a multi-year sequence of climate stress amplified by solar minimums and weakened by prior agricultural stress. The official narrative has greatly simplified the true complexity of the event. It has focused on the most visible, most measurable, most photogenic aspect of the disaster, but in doing so, it has missed the deeper truth about how disruption actually operates in complex systems. This brings us to our current moment and to the uncomfortable implications of understanding 1816 in its full complexity. Modern climate science has calculated that the probability of an eruption as large as Tambora occurring in the 21st century is approximately 16.5%, meaning that there is better than a 1 in 6 chance that such an event will occur before the year 2010. Moreover, the research suggests that future volcanic forcing effects may be substantially underestimated by current climate models, which tend to use constant volcanic forcing rather than accounting for the stochastic or random nature of volcanic eruptions. In other words, standard climate projections may be significantly underestimating the probability of future climate disruption caused by volcanic events. If a Tambora-scale eruption were to occur in the 21st century, the consequences would be compounded by the fact that modern civilization is far more dependent on global food systems and international trade than 19th century civilization was. A crop failure in one region cannot be easily mitigated by surplus production elsewhere, because global agriculture is more specialized and interconnected. A disruption to global shipping would threaten food supplies in regions that depend entirely on imports. The cholera pandemic that followed 1816 killed with 19th century medicine and public health infrastructure. A similar pandemic emerging in the context of climate disruption today would encounter populations that, despite modern medicine, are more densely packed, more mobile and more vulnerable to rapid disease spread. Moreover, the 1816 crisis occurred in a context of one-directional climate concern. The cooling caused by volcanic eruptions was temporary. Everyone understood that the climate would eventually return to normal. Today's climate is changing in a completely different direction. The world is warming as a consequence of anthropogenic greenhouse gas emissions. A future Tambora eruption would not cool the planet back to pre-industrial temperatures. Instead, it would provide a temporary respite from warming, a brief period during which the warming trend paused, only to resume afterward. This would create a deeply disorienting pattern for societies already stressed by adaptation to long-term warming. The window of adaptation would be disrupted by the temporary cooling. Then, as warming resumed, adaptation efforts would have to restart. The net result might be even more chaotic than 1816 itself. We would be attempting to adapt to a moving target, a climate system that alternates between warming and temporary cooling, rather than a relatively linear change in one direction. The fundamental lesson from the year without a summer, when examined in full depth and complexity, is that our understanding of history and climate has been shaped by the need to simplify complex phenomena into comprehensible narratives. We focus on Tambora as the cause of 1816 because volcanoes are dramatic, measurable, and make sense as explanatory frameworks. We focus on 1816 as the disaster year because that is when the visible crisis occurred. But the real story is far more complex. It involves decades of climate stress, cascading biological and social consequences, and the interaction of multiple systems operating at different timescales. And that real story contains warnings for our time. It warns us that the consequences of climate disruption are not limited to the immediate impacts that are easiest to measure. It warns us that cascades of consequence extend far into the future. It warns us that societies that appear stable are often far more vulnerable than we realise, because their stability depends on climate consistency. And it warns us that when that consistency is disrupted, even for a single bad year, the ripples can reshape the world. The year without a summer was not simply a climate anomaly. It was a revelation. It revealed the fragility of human civilization when confronted with forces beyond its control. It revealed the interconnectedness of systems that we often treat as separate and independent. It revealed that disruptions in one domain, the climate, cascade through multiple other domains, triggering disease, starvation, migration, and social collapse. And it revealed something that the people of 1816 could only sense but not articulate, that history is not determined by human agency alone. History is the product of the intersection between human societies and the natural systems that sustain them. When those systems change, history changes, and we must change with it or be swept away. As we contemplate the climate challenges of the 21st century, from anthropogenic warming to the risk of future volcanic disruptions, the year without a summer offers us not a prophecy, but a mirror. In that mirror, we see what can happen when the climate system shifts in ways we have not prepared for, when cascades of consequence extend far beyond the immediate crisis, when societies struggle to adapt to changes they did not expect and did not know were coming. We see the fragility of global food systems, the vulnerability of densely packed populations to disease, the way that environmental stress triggers social upheaval and political instability. And if we look closely enough at that mirror, we see ourselves. Not as we are now, but as we might become if we fail to understand and prepare for the possibility of disruption. The year without a summer was 200 years ago, but its lessons are urgently, critically relevant to our present moment. The question is not whether we will face disruption. History tells us that we will. The question is whether we will be ready or whether we will be caught as unprepared as the people of 1816, staring at a sky without summer and wondering how the world could have changed so completely and so quickly.